Okay, so section 4.6. And we kind of started that. These are nonlinear inequalities. And this section seems kind of like, yeah, nonlinear inequality is fine. But for those of you who are going to move on to other forms of math, that's going to become pretty important. For those of you who are planning on taking Calc 1, you will be faced with solving nonlinear inequalities. And it's really going to be kind of like this huge problem, and then there's this one part you just, hey, solve that nonlinear inequality. That's easy. So we have to get good at that so you don't spend enough, a lot of time on this in the future. But based on what I told you last time, if we understand the concept of multiplicity, how the sign of a function changes around around odd multiplicities, then you're good. Zeros or asymptotes, meaning where your function equals 0 or when your function is undefined. Okay? And then you just have to pay attention to multiplicity. So let me just give you a quick example, something very simple. So x to the power, I don't even care, it looks like 13. X minus 1, x plus 2 squared, x minus 3 cubed, less than 0. Yeah, well, just anything you like as long as it's odd. That's the only thing that matters, the oddness of that number. Um, so again, as I told you, the only time a sign of a function can change is around zeros or asymptotes of odd multiplicity, right? So we decided to give those zeros and asymptotes a special name. We're going to call them critical numbers, where it hits the x-axis or it does the asymptotic thing. So there is a little definition, a critical number of a function. So definition, C is a critical number of f of x if 1, f of c equals 0, 2, f of c is undefined. I need actually both of you. Would you like to come in? These are two other math faculty members. Is solving nonlinear inequalities important in calculus?
Absolutely.
Absolutely.
Yes.
Thank you very much. You can leave.
Yes.
So that's, that's college algebra. So I was trying to explain to them as long as they have to. It's very important. This little thing, this little section is a make it or break it type of situation. But anyways, these are zeros and asymptotes, right? Whatever makes a function equal 0, whatever makes a function undefined, right? Zeros and asymptotes. So when we're trying to solve a nonlinear inequality, first step is to find critical numbers. Actually, that's a second step. I'll tell you what the first step is later. In this problem, we can just go straight for finding the critical numbers. Since this is a polynomial, it only has zeros. It doesn't have any asymptotes, right? So what are the zeros of this polynomial? 0, 1, -2, +3, right? So these are the potential points where the sign of the function changes. Or in other words, I can just grab this function. Can I just grab this thing? We're so good at graphing polynomials. Because what is the degree? 13, 14, 16, 19, right? So it's a odd polynomial. So that's the end behavior. Remember that story? So the x-intercepts are -2, 0, 1, and 3, right? And it's going to bounce off -2. It's going to do the wiggle thing through 0. It's going to go through 1, and it's going to wiggle through 3. But it's not that important whether you wiggle or not. The only question is, when is it above, when is it below the x-axis? Because now we're solving the inequality. So when is it negative? This chunk is negative, then that chunk is negative, and this chunk is negative, right? So the solution here, have to be very careful. It is from -infinity to -2, not including -2, because that's a strict inequality, and then union from -2 to 0, union from 1 to 3. Right? I just chose the negative intervals. Are you okay me splitting that at -2? Because the value of that function is 0 at -2. The question is, when is it less than 0? If I put less than or equal to, if I do it like that, then these two intervals really connect, and it becomes from -infinity all the way to 0. Because now 2 is a part of it. And then bracket from 1 bracket to 3. Does that make sense? So anyway, so this is really, if you understand how to sketch it, then we're good to go. Let me show you how your book will do this. So we found the critical numbers. They are x equals -2, 0, 1, and 3. So then just draw a number line. You don't even need to do a two-dimensional graph. Just do a number line and mark those points. Okay? And then the book will test each interval. They will take a point to the left of -2. They're going to plug it into your function, and they're going to see, is it a positive or negative? And then they'll do it on every interval. So 1, 2, 3, 4, 5 computations that we don't have to do because we understand how those functions behave, right? If you understand that it's an odd degree polynomial, so it has to start on the bottom. So that interval will have a negative sign. And then you just use the multiplicity. -2 had even multiplicity, so the sign stays the same. And then 0 had an odd multiplicity, the sign will change. 1 had an odd multiplicity, the sign will change. 3 had an odd multiplicity, the sign will change again. Right? I mean, really, we're just predicting where the graph goes without graphing it. So the solution is from -infinity to -2, union -2 to 0, union 1 to 3. So that's even quicker. You don't have to draw a graph. You just have to predict where the graph goes. And the reason why I started with the minus, because I understand end behavior. So it starts all the way on the bottom, so it's negative. And then I'll let multiplicity take care of the rest. Isn't that sneaky? I really like this approach. We had, a few years ago, we were using this one textbook by this guy, and the book was just horrendously awful. Except for that part. He was the only one who was presenting this theory using multiplicities, and this is so awesome. So I'm still teaching it like that, because this is good stuff. If that stuff doesn't make sense, you can always pick a point from each interval, plug it in into your function, and you'll get the signs, pluses and minuses. But this is a lot faster. Works with polynomials and rational functions. When you're going to be in your calculus and your function something funky, you'll probably have to test each interval. But for polynomials and rationals, it works like that. And most of the time, you're going to be dealing with polynomials. There'll be a little part where it's something weird, but how is that? You should have one question, though. Yes. What's the first step? The first step is to get 0 on one end. Because if you don't have a 0 on one end, then it doesn't make sense. You want to get 0 on one end, so the question always becomes, is it positive or negative? Not, is it greater than 2x plus 1 or less than 2x plus 1? That's very confusing. So you want all the questions to become, is it positive or negative? So that's that. Step 1 is to get 0 on one side. Step 2, find the critical numbers, and then step 3 is to test the intervals. And then, and then answer the question. The question was, when is it negative? So we just answered that. We see it's negative here, here, and there. How's that? The hardest part of this problem usually is step 1, getting 0 on one end, and step 2, finding the critical numbers. Let me do this example. X minus 3 over x plus 4 is greater than or equal to x plus 2 over x minus 5. Okay? So I want to get 0 on one end. And here's the thing about the inequalities. If this was an equation, then you just go ahead and multiply by the denominators to cancel the denominators out. We cannot do that with inequalities. Because with inequalities, when you start multiplying by something that contains a variable, that variable potentially can be negative, so maybe you have to switch the sign, maybe you don't, we don't know. So we don't want to be doing that. Okay, so with inequalities, you cannot be canceling denominators because, well, first of all, denominators produce those asymptotes. They're also important. So you have to mess with the rational expression as it's written. You cannot simplify it like you do with equations. So this is the first step. Is that being recorded? Yeah. Okay, so we got 0 on one end. Well, in order for me to find the critical numbers, to find the zeros and asymptotes of these functions, I actually have to subtract these two fractions. I have to pull them into the single fraction. So now you have to remember how to subtract rational expressions. So you have to find the least common denominator first. Well, the least common denominator here is the product of x plus 4 and x minus 5, because these are two different denominators, so you need both of them. So that means we have to multiply the first fraction by whatever's missing. So it has x plus 4, you want x plus 4, x minus 5, so we'll multiply by x minus 5, x minus 5, right? While the second fraction is missing x plus 4, so we'll multiply by x plus 4 over x plus 4. Is that okay? Because, with subtracting fraction, you want to have same denominator. So when you pull everything together, in the numerator you have x minus 3 times x minus 5 minus x plus 2 times x plus 4. Right? This is, you multiply the numerators. So the sign in between is the subtraction. So you still have to simplify that numerator. You want to open up all the parentheses, combine like terms, reduce or whatever. We just did that kind of stuff in 055 this morning. So this is something you should do, kind of homework 0 type of stuff. You did that on homework 0, adding or subtracting rational expressions. But anyway, so you should be good at that. So I'm going to move fast. I'm going to FOIL. So if you FOIL the first one, you should get x squared minus 8x plus 15. FOIL and combine like terms. That's what you should get. On the next one, you'll get x squared plus 6x plus 8. But then there's a minus in front. So you'll end up with a negative x squared minus 6x minus 8. So I'm kind of skipping a few steps here with the assumption that you are good at foiling and all that stuff. The way I foil, the same way you factor, two numbers that add to 6 and multiply to 8. So I know to add 4 and 2 to get 6 and multiply 2 and 4 to get 8. So combine like terms, x squared cancel, and what we end up with? Negative 14x plus 7 over x plus 4, x minus 5 greater than or equal to 0. So you have to do all that in order to find the critical numbers and have 0 and 1, and otherwise this is a very weird problem. But when you have 0 and 1, and then the question is, when is this thing positive or 0? So critical numbers are, so the zeros here, whatever makes the numerator equal 0, which is positive 1/2. Do you agree with that? Positive 1/2 makes the numerator equal 0. So that's a 0 of that function. And the asymptotes, the vertical asymptotes, are, well, negative 4 and positive 5, right? All multiplicities are singles, so the sign will alternate at each one of those, right? I mean, I've been saying this for over a week now. So really, all we need is one sign. If I figure out the sign at one of the intervals, then I can do the rest by alternating it. So I'm going to put my critical numbers here, negative 4, 1/2. Yeah, so that's how we do zeros of rational functions. Whatever makes the numerator equal 0. Okay, so here it is, right? Something like that. I mean, all I need is one sign, okay? That's all I need. So usually one thing that's easy to test is pick 0, right? 0 is not taken. What if I take x equals 0, so it's on this interval? I'll plug 0 into my function. I get plus 7 in the numerator, right? Positive, positive, and a negative. So overall, what is it going to be? Plus, plus, and a minus. Negative. So I know that this function is negative on this interval. All you need is just one interval. I decided to pick 0. You could have picked 44, right? Take 44, plug it in there, something negative. So negative, positive, positive, so still negative on that interval. Again, any number that's not taken yet. I chose 0 because it's usually easy to plug in. But then since we agreed that all multiplicities are ones, the sign will just alternate. So I don't have to do anything else. Is that okay? We didn't have a single critical number with even multiplicity, so I can just alternate the sign. So now let's answer this question. When is this expression greater than or equal to 0? So here, right? That's where it's positive, and there. The only thing you have to be careful is the equal 0 part to make sure to include 1/2. Because 1/2 makes it 0. Do not include 4 or negative 4 or 5. Cannot include the asymptotes because they make it undefined. Shouldn't be part of the solution. But include the zeros. So the solution here is from negative infinity to negative 4 with the parentheses. Cannot include negative 4. Makes everything undefined. Union bracket from 1/2 to 5 parenthesis around 5. So again, no matter what, you cannot put a bracket around the asymptote. Shouldn't be including those numbers in any kind of a solution. So the hardest part of this was actually pulling it all together into one fraction. The rest is kind of what we did. It kind of saves a little bit of time. You don't have to sketch the full graph. You don't have to worry about the horizontal asymptotes or anything like that. This is just predicting what the graph is going to be, right? questions on this? Whew. There's a fun one at the end, apparently. Does the concept make sense? And you can really sketch the full graph every time and then see where it's above, below. It's a little bit extra work. You don't have to do it here. You just need to make a prediction. All right, here's another one. X cubed plus 3x squared minus x minus 3 greater than or equal to 0. So first, polynomial, 4 terms, nothing in common. I want to find all the zeros, so I should be factoring that thing. How do you factor that thing? By grouping. So you look first 2 terms, pull out the x squared, leaves you with x plus 3. The next 2 terms, pull out a negative, leaves you with x plus 3. Okay. So x plus 3 now becomes your common factor. So you pull x plus 3 out, right, it comes out, and you're left with x squared minus, well, placeholder 1. Factoring by grouping. And then x squared minus 1 also factors. So we see all the zeros of this polynomial. We see all the critical numbers. X equals 3, x is plus or minus 1. These are the 3 critical numbers. Is that okay? Okay, so all I have to do now is to test the interval, -1, 1, and 3. Yes, -3, you're right. Thank you. So then, -3, -1, and 1, yes. Okay. So I don't even have to, again, you can always take 0, plug 0 in there, see what you get. Or you can play with the end behavior. That's an odd degree polynomial, so it will start all the way on the bottom, so that end has to be negative using the end behavior, right? Looks like a cubic. Everything has single multiplicity, so the sign will just alternate. You just need to get one sign, end behavior, and then you alternate the sign. And that will be the graph of that function. Are you okay how I'm producing those little pluses and minuses? All you need is 1, and then you use multiplicity. How you get that one sign is up to you. I used end behavior. You could have taken 0. 0 is here. Plug 0, you'll get -3. That's your y-intercept. So it's negative over there. Then you alternate because of the multiplicities. Right? Now, what is the solution here? Question was, when is this greater than or equal to 0? Greater than or equal to 0. So when is it positive or 0? That's negative over there. So from -3, brackets or parentheses? Brackets, because including 0, union 1 to infinity. Right? And that's it. Not too awful. This looks awful. Unless I'm making a mistake. Any questions on this? So you have to be good at that intermediate algebra type of stuff, factoring and adding fractions, all that homework zero type of fun stuff. Because the new material is real. I mean, this is new right there. That's what I just taught you. And I didn't even teach you. I just made you connect few earlier concepts together. So there's really nothing new. The hardest part is either factoring or doing these algebraic manipulations, which we're really going to kick our butts on this one. So I have these two things less than or equal to 2x over x squared minus 6x plus 5. So again, we want to get 0 on one end. And eventually combine all these three fractions into one, because then we'll see all our critical numbers. In order for us to do that, we have to find the least common denominator, right? And in order for us to find a true least common denominator, we really have to factor everything. Otherwise, you're going to end up with a 6-degree polynomial, and the denominator is going to be a nightmare. Let's factor everything. It's going to be a lot smaller. So, as we move through that, how do you factor the first one? X plus 5, x minus 1, plus 3 over difference of squares, x minus 5, x plus 5, minus, I'm moving that other thing over, so change the sign, 2x over, how would you factor the third one? You only get a minus in the middle. Minus 3 minus 2. No, that doesn't work. Two numbers multiplied. Minus 5 minus 1. Because if it was minus 3 minus 2, then we're in a big world of pain, because everything is really different. But this way, we only have three different factors, right? We have x minus 5 there a few times, x plus 5 there a few times, x minus 1 there a few times. So the LCD is really x plus 5, x minus 5, and x minus 1. That is the least common denominator, right? You're just taking all distinct factors. So if you look at the first fraction, and you look at the denominator and you compare it with the LCD, what is missing? Which factor is missing? X minus 5. So we'll have to multiply this one by x minus 5 over x minus 5. You do the same thing with the second one. What is missing? X minus 1. So you multiply by x minus 1, x minus 1. And you look at the third one, and it's missing x plus 5. So you multiply by x plus 5 over x plus 5. So now they all have same denominators. They can be put together into a single fraction. I don't even care what the denominator is. I'm just going to write an LCD. And then it's x times x minus 5 plus 3 times x minus 1 minus 2x times x plus 5 less than or equal to 0. I have to open up all the parentheses, combine like terms in the numerator. I'm very happy with my denominator. I'm not going to touch it. It's nice and factored, gives me probably 3 asymptotes. But in the numerator, we get x squared minus 5x plus 3x minus 3 minus 2x squared minus 10x all over the LCD. Combine like terms. X squared minus 2x squared is negative x squared. negative 5x plus 3x minus 10x is what? Minus 12x, and then a lonely negative 3. Right? I see the 3 asymptotes. I already see 3 critical numbers. It is negative 5, positive 5, positive 1. These are the 3 critical numbers at which the sign of this function will change, because all have single multiplicities. I see 2 more in the numerator, because that's a quadratic, probably has 2 solutions. So I need to find those. So I have to really solve this equation. My zeros of the numerator. Too many minuses. Make them all pluses, right? Because when it's an equation, then it doesn't matter. Here you would have to flip the inequality, but or you can solve this equation as it's written. You know, however you solve that numerator is really up to you. I can solve it as it is. I can change all the signs, because if you just multiply both sides by negative 1, all the signs change. But we see I won't be able to factor this, so I have to use the quadratic formula, right? X is negative 12 plus or minus the square root. 12 squared is 144 minus 4ac, so that's 12, right? Over 2. So it's negative 12 plus or minus the square root, what is it? 132 over 2, right? 132, I believe, is 4 times 33. That's 132. So I can simplify that square root. Negative 12 plus or minus negative 12 plus or minus 2 square roots of 33 over 2, right? You take the square root of 4, and you divide everything by 2, you get negative 6 plus or minus the square root of 33. Whatever those numbers are, I don't care. Those are 2 more critical numbers. Yeah. Yeah? You just multiplied everything by negative 1. I just, for some reason, I never liked having a minus in front of the square. I don't know why. I'm prejudiced against the minus. Again, you could have plugged in this into the formula as it's written. Would it? Yeah, you'll get the same answers. Yeah, you'll get the same exact answers. Yeah. It's just, it'll be a little harder to keep track of all the negatives. But you get the same exact answer if you solve it as it's written. So anyway, so I have 5 critical numbers. My critical numbers are, so the zeros of this function, negative 6 plus or minus square root of 33, and the vertical asymptotes are x equals plus or minus 5, and x equals what? Positive 1, right? Yeah, positive 1. Because it's x minus 1 as a factor. Okay, are we good? I don't really care what those numbers are numerically, because I can still place all of these numbers onto my number line. Because look, here is negative 5. Let's say this is positive 5, and this is 1. Not drawn to scale, who cares? Well, think about this. Negative 6 minus square root of 33 is going to be to the left of negative 5, right? Because it's already negative 6 minus some other number. So here's negative 6 minus square root of 33, right? Now, what is the square root of 33, roughly? Between 5 and 6, right? So negative 6 plus something between 5 and 6 is something negative. Yeah, so you get negative a quarter, so it's somewhere here. Negative 6 minus, I'm sorry, plus square root of 33, and it's to the left of 0. The 0 is here somewhere. Okay? So all I need is just one sign, and then I'll just alternate them, because all multiplicities are odd, right? So I really need to test one of the intervals. So let's see. Well, where's my function? Here's my function, right? Let's take 0. Let's plug in 0. 0 is always easy to plug in. If I plug in 0, I'll get negative in the numerator, right? Minus, plus, minus, and a minus. So 3 negative signs. What is that going to give me? Overall, a negative or a positive? Negative. If you have odd number of negatives, it's a negative. So that means on the interval from that silly square root and positive 1, it's going to be negative. The interval that contains 0 produced a negative result. So then the sign will alternate everywhere else. Because all the multiplicities were single, nothing doubles up. So the question was less than or equal, right? So less than between negative 6 minus the square root of 33, putting a bracket around it because that's a 0, all the way to negative 5, put a parenthesis, because negative 5 is an asymptote, cannot include that. Union, again, from that square root to 1, not include 1, because 1 is one of the asymptotes, and then union, parenthesis, from 5 to infinity. Don't include 5, because 5 is one of the asymptotes. How's that? That's the answer. So again, the hardest problem usually is finding those critical numbers, because you have to do some earlier algebraic style of math when you manipulate things. So any questions on this?
So you know how you always get fully with that whole single multiplicity, so you know it's not just switches. Like so you're saying that if it's just like x squared plus x plus just a normal function, you automatically get like you do so fast that it's just gonna
Yeah, because again, I'm looking at all these zeros, right? I'm looking at all these factors in the denominator. They all have single powers. And my quadratic in the numerator also produced 2 separate answers. So all the answers appear there exactly once. So that's the multiplicity idea. So odd multiplicity sign changes. If I put a little power 2 over here, it will just show me that around 5, the sign stays the same. So we will do the same process. We would plug in, let me update the number line. So what did I just do? Where is it? I lost it. Here it is, right? So not part of this solution. Same numbers, negative 6 minus the square root, right? Then negative 5, then negative 6 plus the square root. Yeah, 1. And I also need another one, right? There's a positive 5 somewhere. Oops. There's a positive 5 somewhere here. I would do the same way. I will still take a 0, and I'll plug 0 in here. My numerator comes out negative, right? That comes out positive. That comes out negative but squared, so that's still positive. So it's a negative, positive, positive, and negative. So only 2 minuses. So that produces a plus. So it stays positive on this interval, right? Then it changes the sign here, but it stays negative over there because positive 5 came from this region of even multiplicity. But then the sign changed everywhere else. So then your solution clearly changes, but it does not affect the critical numbers per se. Okay? Does that make sense? So that's, again, that's that concept of multiplicity. And if you understand that, I'm going to try to erase all of that. One more. Nope. Here we go. So if you understand that idea, then it's really quickly. If you don't, again, you have what, 6, 7 intervals. Just pick a number from each interval and figure out the sign of your function. Again, all you need is a plus or a minus. So you can literally go, okay, it's a minus, plus, plus, minus. You don't need to know the exact value. You just need to know the sign. That's the benefit of keeping 0 on one end. Makes it a lot easier, right? And then you alternate around odd multiplicities. Keep the sign around even multiplicities. Good stuff? All right, so that's your chapter 4. So you see, we're about half a day ahead of schedule. I'm starting chapter 5. Don't get all comfy. Oh, yeah. I want to keep us ahead of schedule so we can, if necessary. Because, we still don't have a quorum for you to vote to go home. So I get to do whatever I please. Not like when we have a quorum, you get to vote. I'm just... So, okay, chapter 5. I'm going to talk a little silly at first. Chapter 5. Chapter 5 introduces a whole new family of functions that we haven't dealt with before. Everything that we dealt before called kind of algebraic functions, those ones are a little iffy because solving equations with those functions, because again, the whole purpose of everything we're doing is to solve equations, well, occasional inequality. That's all we do. Let me give you an equation. Don't write anything down. This is more of a motivational speech. Here's a simple equation. 2 to the power x equals 8. We haven't seen equations like this before where the exponent becomes the unknown. We haven't seen anything like that before. But you can probably guess your answer, right? You can guess the value of 3. What do you think 3 is? Did I say 3? I already gave you the answer. What do you think x is? 3, yes. Because 2 cubed equals 8, right? That's easy. But if I change this ever so slightly, yeah, it's probably less than 3, probably bigger than 2, somewhere between 2 and 3, maybe closer to 3. But I want you to give me the answer to like 5 decimal places. Then, that's hard. You cannot do this in your head. So we need to somehow, and there's nothing you can do algebraically. You cannot subtract something from both sides. You cannot divide by whatever. You cannot take the x root of both sides to kill the power x, because that makes no sense, right? That shouldn't make any sense. Because then you're stuck with the x root of 7. What the hell is that? So we're stuck. We don't have any algebraic tools to get the x by itself. Because again, the whole purpose of algebra is to have this. X equals something nice, right? Now our x is shoved all the way into the exponent, and I cannot really get to it. That 2 blocks me or whatever. However you want to think about this, you cannot solve this equation, basically. That's what I'm saying. If I ask you, give me the solution to 5 different places, unless you know how to solve this equation, unless you've been, well, yeah, whatever that means. But most of us either solve, and all of you might have seen it before, but don't remember. We have to come up with something fancy. All right, good. Yeah, I will have to use logarithms of sort, but we understand that the tools that we have at this stage are not enough to solve that equation. Okay, now on totally unrelated note, Totally unrelated note. Consider these two functions. I don't know if whether you want to be writing this down. It's really up to you. It's still more of a motivational speech. You've seen me play with these types of functions in chapter 2, maybe. So here are the two totally random functions. And I want us to take the composition of these functions. This is the thing I forgot to put on your test, make you do some compositions. And I regret that. But you remember how to do the compositions? And this really means f of g of x. So you take the whole of g and you put it inside of f. So that becomes 2 times something cubed minus 7. That something is the g function. Right, that's the idea. And then you follow the order of operations. Cube root and power 3 kill each other. You're down to 2 times x plus 7 over 2 minus 7. Right? Then 2's cancel each other. And we're down to x plus 7 minus 7. And we're down to just x. Oh, that's lovely. Right? So that's the composition of these two functions. This happened to be x. And I've done examples like this when we learn compositions. I kind of made you play with that. And I kind of told you that's kind of a big deal that it just came out like that. The bigger deal, if I take composition the other way, if I put f inside of g, so the other way of composition. So what happens here is it's a cube root of, instead of x, I'm going to put f, which is 2x cubed minus 7, right? Instead of that little x over here, I put function f. But then I continue with a plus 7 over 2 under the root. So 7 and a 7 cancel. We're left with a cube root of 2x cubed over 2. 2 and a 2 cancel, right? So that leaves us with a cube root of just x cubed, which is x. Okay. We're good? Remember how to do compositions? Well, think about what just happened. If I plug, anybody have a number in mind? Three, okay. So let's take 3 in for x. F of 3. So if I take 3, 3 cubed is 27, times 2 is 54, minus 7, 47, right? F of 3 is 47. But if I take that 47 and I plug it into g, I'll get the 3 back, because that's what it says here. If you take a number, put it in one function, take that number, put it back into the second function, you're going to get what you started with. And try, if I put 47 in for x, 47 plus 7 is 54. 54 divided by 2 is 27. Cube root of 27, 3. Right? So you kind of complete the full circle. One took you from a domain to a number in the range. The other one took that number from the range, put it back into the same spot from the domain. Ooh, does that make sense? But the big idea here, if I ask you to solve for x, and the equation was a cube root of x, what is it, x plus 7, was it? X plus 7 over 2 equals, I don't know. What's your favorite number today? 6. Okay. We can solve this equation. We have enough tools to solve this equation, to dig the x out, right? How would you dig the x out? You will cube both sides, you will multiply by 2, then you subtract 7, right? You just precisely described that function. Cube, multiply by 2, subtract 7, right? So there's a sneaky way of solving this equation, is to take composition, apply f to both sides of this equation. So remember, the cube root was the g function, and the f function is that 2x cubed minus 7. We already showed that the left-hand side, when you take the composition of these two functions, equals x in one move. Right? That's all that mumbo jumbo. Because I know if I take the composition, here it is, I'll get x. All on the other side, it is 2 times 6 cubed minus 7, right? Which is a number. So I just solved that equation in kind of a one move. Didn't I? I know there seem to be many more moves before that. But really, as far as solving this equation, if I know beforehand that composition of these two functions provides me, just gives me the x, then I take the, I take the same composition on the other side. So whatever this 6 cubed 192, what? 216? 216 times 2, 432 minus 5, 225. That's a pretty number. Is that right? 225. So that's the solution to that equation in one move, right? If beforehand we knew that these two functions have this property, we can solve these types of equations in one move. Total overkill for this equation, okay? But you might wonder, if I go back to this problem, if there is a magic function such that if I take the composition on both sides and the left side just spits out the x, because we just kind of did that whole unravel thingy, well, on the other side, I just have to evaluate that function at 7, and I just solve the equation. Who cares? You're probably right. Yeah, 425, because you double 216, it's 425. It's not an important issue here. This is more of a theoretical mumbo jumbo. But yes, thank you for paying attention. How much sense am I making at the moment? That sometimes to solve equations, you can just explode one side to just turn it into x. That's what I'm doing. I just blew one side up x in one move. That's your, that's what you always wished for. So the whole equation just go boom, x. And the other side is some magic number, right? That's what we're trying to accomplish. So before we even start talking about solving equations of this type, we need to see, well, what the heck happens here? How can I find these magical pairs of functions that when you compose them, you just get out the x by itself? These pairs of functions are called inverse functions. These functions are inverses of each other. One is the inverse of the other. So it does the exact opposite of whatever the other function is doing. If you think about this, the exact opposite, meaning opposite operations, opposite order of operations. Let's try this one. What is the order of operation? Cube, multiply by 2, subtract 7, right? Well, yeah, we'll do that, but on this one. Yeah, so cube first, times by 2, subtract 7. This is the order of operation here. The inverse function will reverse the order and the actual operation. So instead of, the last thing we did is subtracted 7, so the first thing we're doing is to adding 7. Add 7 first, multiply by 2 second, divide by 2 second. Cube was the first step, cube root the last step, if you do the order of operation. So you're really reversing the order and reversing the operation itself. It's kind of like, this is the way you can guess the inverse of a function. The way you make sure that two functions are truly inverse of each other, they have to satisfy this. The composition of both functions, either way, has to produce an x, both ways. Okay? Sometimes we'll see when you get x and when you compose it one way, but you compose it the other way, you get something other than x. So we'll deal with that. Well, another issue is to really think, do all functions have inverses? Can I just invert any function out there? And that's a whole other issue. And we'll try to talk about that. So I think that's enough motivating you I'm about to start doing some actual tangible examples. Does that make sense? No? That's okay. This is more of a motivation. Again, so the motivation is to explode a function. That's really what's going on here. I want to turn one side of the equation into just one variable. Okay, so basically that's what we start with section 5.1, inverse functions. So the idea is this. So you have two sets. You have a set A, that's our domain, and you have a set B, that's our range. So a function will take a point from the domain and will turn it into point in the range, right? So that's what a function does. The inverse function of that function will take that same point from the range and will place it back into the domain. So that's what the inverse does. So this is why the composition always results in x. If you do the composition, apply f first and then apply the other one, you're back where you started. Or go the other way around. Apply the green one first and then apply the blue one, you're back where you started. That's kind of the idea. Now, so this is the inverse. We have a special notation for inverse functions. We use a little, which looks like an exponent, -1, but it's not an exponent, this is a notation. So when you see something like this, that stands for inverse function of f. Or f inverse, depending how you want to call it. Okay? So basically a definition, f and this thing, f inverse, are really inverses of each other. If and only if, remember the double F, if and only if, the following two concept holds. If you take the composition, f of f inverse, you get x. And if you take the composition the other way, you also get x. So the composition of both functions results in x every time. If that happens, the two functions are inverse of each other. Okay? So when we're going to try to solve that equation, 2 to the x equals 7, we're going to build a new function with that property in mind already. So we're going to know that new function satisfies that definition. So we can solve a little more complicated equations. Okay. So let's play a little bit. A few examples. F equals 3, 5, 2, 4, 7, -1. Here's a nice little function, right? Is it a function, first of all? Whatever this relation is that a function? I mean, I told you it's a function, but why is it a function? That was the first question of on your exam. Why is this a function? What are you looking at? Yeah, but right. So you don't want to see repetition in the x. You don't want to see the same x value going to different y values, and we don't see that. Right, so that's a function. And I can ask you, what is f of 3 equals 2? What do you think that is? F of 3 equals what? 5, right? F of 2 equals 4, f of 7 equals -1, F of 11 is undefined. I don't know, right? Here's an equation that you can solve. F of x equals 4. You have to solve for x. What do you think the x is? 2, right? Which ordered pair came from? So I gave you the y value, x equals 2. Well, the inverse function of this function, the f inverse, is actually the same ordered pairs, only in flipped order. It is 5, 3, 4, 2, negative 1, and 7. So the order of x and y changes. And that kind of makes sense. I mean, all I did, I just flipped x's and y's. So domain and range got interchanged. That's the idea. And if I go back to that picture I drew, for function f, the domain was a and the range was b because it was going from a to b, while the other one was going from b back to a. So the range became the domain and domain became the range. That's an important concept there. Range and the domain switch. Very good. Yes. And this is what I was going to do in about 5 minutes. So you're preempting my presentation. But yes, you're right. If I don't write this down too early, you're not ready for this example yet. But this is a function, right? Everything nice and friendly. You know, everyone's happy, nothing wrong. But when you start flipping that, you're going to get 5, 3, and 5, 2. Well, that's no longer a function. So this function does not have an inverse. That is a function itself. Okay? So we'll have to get a little careful. We're going to define a concept of a one-to-one function, and only those have inverses and so forth. But yes, you exactly on the money. This is going to be a problem for us, a fixable problem. We'll be able to work around it somehow. But yes, you're absolutely right. This is going to be an issue. Okay, so let's play the game. I want to play a game. This is an exciting game called Guess the Inverse Function. And I kind of told you how to guess it, right? You reverse the order of operation, and you reverse the actual operation. So, guess the inverse. That's an exciting game. You don't get to win anything. But it's just feel-good points. That's what you get to win. 2x. That is a nice function. The function of this function is to multiply stuff by 2. Right? Just doubles everything. Well, what do you think the inverse of this function is going to do? X over 2 will half everything. So it does the opposite operation. Since there's only one operation, so you just do the opposite. One is doubling, the other one is halving everything. How do you check whether your answer is correct? Well, you take composition. Right? If I take composition of both functions in both cases, the answer should be x. And it is, right? Let's do it kind of mentally. 2 times x over 2 is x, right? But then 2x divided by 2 is also x. So whichever you compose, you get x. So we're good. So we able to guess that one. How about this? F of x equals 3x minus 4 over 2. Can you guess that one? I'll give you a minute. No. But you kind of starting it correctly. Well, what is the last thing this function is doing? The last operation. What? Divide by 2, right? You plug in a number, you multiply by 3, then subtract 4, then divide by 2. So what is the first thing this function going to do? Multiply by 2. Multiply something by 2, so 2x, right? So you had that 2 times something. Well, what was the second step here? 3x minus 4 over 2. What is the second thing? Minus 4, so the second thing here, plus 4. The first thing here was times 3. So what is the last big operation? Divide by 3, like that, right? So everything is divided by 3. That's just a guess. And that was kind of weird, right? And we'll have a nice algorithm. We'll be able to find them pretty fast. It's not that hard. I'm just trying to make you do so many steps in your head, and it's a good game, but it's not really the way you want to do that. Well, let's test. If I take the composition, if I do f of f inverse, so that's 3 times whatever it is I believe the inverse is, minus 4 over 2, right? That's the composition. So simplify that. 3's and 3's cancel. We're left with 2x plus 4 minus 4 over 2. Right? 4 and a 4 cancel. 2x over 2. 2 and a 2 cancel, so we get x. Right? Well, we'll have to do it the other way as well. Because again, we'll see example, at least one, where it works one way, it doesn't quite work the other way. So the other way, if I do f inverse of f, so that becomes 2 times 3x minus 4 over 2. What am I plugging? I've already lost. Plus 4 over 3, right? I'm plugging it in here. So again, following the order of operation, 2's cancel. 3x minus 4 plus 4 over 3. Right? Then 4 minus 4, they cancel. You're down to 3x over 3. And then 3's cancel, x. So our guess was correct. Right? All right, we're kind of winning at this game. You have, self-respect points, or whatever you call those. But let me do this. I want to do some graphing, because, we cannot food lot. What? Food network. Where's my food plot? Here we go. We had this 2x, that was one function, and the other function was x over 2, right? So that's not a true scale. This goes from -7, -6.5. Can I make this window? Just do -5, 5, -5, 5. That's still stretched. Well, anyways. And I'm gonna do another graph here. Just x. What do you notice about the graphs of the black line and the red line? Is there some kind of a symmetry between the two black lines with respect to the red line? Do you see how if my squares were actual squares, if this was a kind of a pretty not stretched graph, but even here, if you fold around the red line, these two graphs overlap, right? If I do it with the other pair of functions, what were they? 2x plus 4 over 3. And I'll do, what was the other one? 3x minus 4 over 2. Kind of the same thing, right? And they intersect on that point. The intersection happens on that red line. And what is that red line? That line is y equals x. right? Just y equals x. And this symmetry kind of makes sense because we did, the inverse in the function, that flipping of x and y. So it means you should have a symmetry around the y equals x. That's where the flippage occurs, around the line y equals x, because you're switching x's and y's. One point, if a function has a point 7 and 6, here's the point 7, 6, right? The inverse will have a point 6, 7. Here's a point 6. Well, that's a 7, right? Because it's between 6 and 8. So we have that kind of a flippage. Oh, good. Drew the dot. What was the thing with the cube roots? 2x cubed. What was that example? One of the earlier ones. 2x cubed minus 7. Whatever that is. And what is the other one? X plus 7 over 2. Right, so cube root. So this is a cube root, power 1/3. See, we have the same scenario. One graph and the other graph is symmetric with respect to the line y equals x. And they intersect on that line as well, right? So we'll have this kind of pattern. If I give you, here's a graph of a function, sketch the graph of the inverse of that function, all you have to do is to draw a line y equals x and flip it over that line. Okay, let me do an example of that. So given the graph y equals f of x, sketch the graph of y equals f inverse of x. And again, all I have to do is to whatever is given to me, I have to flip around the point y equals x. So for example, if I have this function that has this point looks like -2, -1, then it has this point at 1, then it has this point, let's call it, what does it look like, 2, 3. So I have this function, this is f. If I want to sketch the inverse of f, I'm going to do two things. First, I will plot the reverse points. So this point was -2, -1. If I flip the order, I'll get -1, -2. This point is going to be on the inverse function. Remember the flipping the order. The point 0, 1 becomes a point 1, 0. And the point 3, 2, 2, 3 becomes 3, 2. And here's the line y equals x. Right? So all I have to do, I need to connect these dots so it kind of appears that I just flipped over that line. But the easiest thing is, if you already have some reference points, sketch them in a reverse order, and then pretend that it's flipped around that line, y equals x. So this green line is the graph of the inverse function. How is this? Is that okay? So just remember that. So the graphs of a function that's inverse are symmetric with respect to the line y equals x. And the way we sketch those graphs, if you have few points, then reverse the order of x and y, sketch them, plot them first, and then, do your best artistic performance on the rest of that. Good? All right. Okay. Well, you know what we haven't done in a while? We haven't played the game that Guess the Inverse game. Remember that game? You liked it so much? Let's play some more. More of our favorite game. Game. Okay. Got away from me. Yes.
That should be the name of our math class.
Yeah. More of our favorite that. Can you guess the inverse? Should be pretty easy, right? Cube root, how confident are you in your guess? Very confident. How can you be 100% sure whether that's the right guess? Yeah, you do the composition. So if you do the composition, f of g of x is the cube root of x cubed. That's x, right? We're all happy. Good. And if we do the composition the other way, it is the cube root of x cubed. And what is that equal to? Are you sure? Confident. All right, good. All right, x, both cases. Therefore, these two functions are inverses of each other. We're good. So good guess. Happy? Yeah. There's another one. So the function of this function is to square stuff. Can you take a guess of what the inverse is? Square root. That sounds reasonable. Everybody's happy with that guess? How can be certain? Plug it in, do the composition. So if I take the composition this way, f of g of x, that is the square root of x squared. What is that equal to? X. Are you all comfortable with that? Everyone's happy? Square root of x equals x? I'm sorry, square root of x squared equals x? Yes? I mean, that's the whole idea behind solving equations that involve square roots. Because if you square it, it goes away. But if you go the other way, and you are faced with the square root of x squared, what is that equal to? No. Well, absolute value of x, because it has to always come out positive. Because if you plug in negative value for x, let's say negative 5, well, your square becomes positive 25, your square root becomes 5. So the negative sign goes away. So, not quite, right? So no, bad guess. Well, good guess, but didn't work, right? Because remember, in both cases, we just have to have the same thing back. Didn't work. So these two functions are not inverses of each other. So, I shouldn't even use that inverse notation there. It makes it kind of sloppy. Okay? But, that this is kind of a bad news because, x squared is one of our favorite functions, maybe, right? You'll enjoy your x squared. And the x cubed had an inverse, so what the hell? And it's kind of going back to what you were talking about. So not all functions have inverses. So if we, where's my, if we have a function, as you were saying, is it have, if it's a function, but it takes two different points, okay, that's not a function, 12, here we go. If it takes two different points to the same y value, it's a function, but I won't be able to invert it. Because if I take the inverse and if I flip the order, this is a problem. That is not a function. So only functions that do not have that repetition in the y actually have inverses. So first of all, it does not have any repetition in the x, and so that makes it a function. And then it does not have any repetition in the y, and that makes it an invertible function. We call those functions one-to-one functions. For one x, you get one y, and boom, that y is already taken, nothing else goes to that y. All right, so that's the definition of a one-to-one function, so that's the trouble. Definition, how did I phrase it before? So a function f is a one-to-one function if for every y in the range there is exactly one x in the domain. So another way of saying this, no repetition in the y or if x1 is different from x2, then f of x1 is different from f of x2. That means if I plug in two different inputs, two different x values, I'll get two different y values. Doesn't work with the x squared. You plug 2, -2, both produce 4. Right? Violates this little thing. Right? Two different inputs have to produce two different outputs. Or you can always say it this way, it's really going to be weird. If f of x1 is the same as f of x2, if you do see two same outputs, then they better come from the same input. So you're basically staring at the same point twice. Then x1 equals x2. But again, the idea is for one unique x, you do get the one unique y, and that y is not taken by anything else. So if the inputs are different, then the outputs are different. Okay? So our domain range picture is very pretty. So if this is a domain and this is the range, then the function will do this. This is a one-to-one function. For one x, you get one y, and that y is not taken by anything else. So when you go in reverse, the inverse function takes us back. That's what the inverse does. Right? In this diagram, what is the domain of f? What is the f start? What is the domain of f? A, right? That's the starting point of f. What is the range of f? B, right? So f goes from A to B. Domain of f is A, range of f is B. What is the domain of the f inverse? B. That's where the f inverse starts. What is the domain of f inverse? I'm sorry, the range. A. So those two flip, right? As we expected, x and y flip. Do you remember the days where I told you we can always find the domain of a function, but in order to find the range of a function, we need to see a graph? Remember that? I told you. So if you see a graph, you look at the y-axis, you're going to, okay, that's the range. Well, now, in order to find the range of a function, you can first find the inverse of that function and find the domain of the function inverse. Domain of the inverse is the range of the original function. So we just came up with a sneaky way of finding ranges of functions, provided there is an inverse. Louis got it. He's very excited about that proposition, right? Yeah, you understand what I'm talking about. Yeah. Given a function, you can always find the domain. never the range. Range is hard. You don't see the range. But if you can find the inverse of a function and then you find the domain of the inverse, all of a sudden you know the range of your original function. That's exciting. It's so important, I'm gonna write this down. So here's the big definition. I already kind of gave you a little definition. So here's the big, what? Big definition? Big words. So here's the definition of this whole inverse function concept in just one kind of sentence. So let f be a 1-to-1 function with domain A and range B. Then there is a function labeled as such with domain B and range A so that the following two hold. If you take the composition this way, you get X, and if you take the composition that way, you get X. That's the big definition of the inverse. It incorporated everything we just talked about. The one-to-oneness is there, and the fact that domain of one function is the range of another function, and the range of one function is the domain of another function. Right? I don't even think I'm going to write this down. We're just going to talk through this. If I give you a graph, just any graph, and I ask you, is this graph of a function? How can you tell whether it's a graph of a function? Vertical line test, right? This is how you test that there are no repetition in the x. Well, take it further. How would you test if there is no repetition in the y? What do you think? Horizontal. So to test whether a graph of a function, whether a function is one-to-one, just looking at the graph, just do a horizontal line test. So if every horizontal line intersects at one point, then you got yourself a one-to-one function. So when you look at the parabola, that x squared we played with, it fails the horizontal line test. When we looked at the cubic function, it passed the horizontal line test. So this is why the cubic function, we were able to guess the inverse, and it worked. But for the quadratic function, that didn't quite work, because it failed the horizontal line test. Who's with me on all of that? Yeah? You very happy and confident? All right, let me mess with you. May I? Let's go back to guess the inverse game. You're just enjoying it too much. Right? Is this a one-to-one function? Think about the graph of the square root. What? What is the graph of the square root function? Like that? That's the square root of x. Is that going to pass the horizontal line test? Yeah, so it is one-to-one. Therefore, it has an inverse, right? Guess. What do you think that inverse is? Well, now think about this. The graph of the negative square root of x is this, right? This is the negative square root of x. Remember how we agreed that the function and the inverse should be reflected over the line y equals x, so that didn't quite work, right? If I flip it, I get something else. You did the reflection around the x-axis, so that didn't work. Well, let's take it further. What is the domain of the square root of x function? Positive and 0, right? All non-negative numbers from 0 to infinity. What is the range of the square root of x function? You know, here's its graph. What is the range? 0 to infinity, the same thing, right? We also know that the inverse of this function exists because it's a one-to-one function. It's got to have an inverse. I know the domain of that inverse, and I know the range of that inverse, right? Remember how the range becomes domain, domain becomes range? So because they're the same, but I'm going to color code it. The domain of this function is from 0 to infinity, right? The range became the domain, and the range of this function is from 0 to infinity. And this got to be the graph of that function, right? What does that look like? It's the same shape as the square root of x, only flipped sideways. So the square root of x will have points like 1, 1, and then we'll have a point 4, 2. So the inverse will have a point, I cannot draw there, but we'll have a point 2, 4. Which function takes 2 into 4? X squared. The inverse of the square root of x function is x squared, only with kind of a limited domain. Not the full x squared, only half of it. Okay? And we can actually do that. We can take a function that's not one-to-one, and we can just cut a piece of it that is one-to-one, but we want that piece to span the entire range of a function. So the square root of x has two identical pieces. So if you want to invert the square root of x, you only take the positive side of it, and then you don't need to worry about the absolute value issue because everything is positive. But that's the idea. Sometimes you can take a function and you can cut half of it. So we call it the domain restriction. You're restricting the domain so the function remains one-to-one. Does that make sense? And then we can find its inverse and so forth. Here's an example. You're going to like this. So restrict the domain, restrict, right? And let's say the function is f of x. I'm going to do something friendly. So do you agree that that's just some parabola? And we're going to restrict the domain basically where the vertex is. So all I really have to do is to find the x value for the vertex. That's going to cut the parabola in two equal pieces. I'm just going to take one of those pieces. Remember how to find the vertex? For the vertex, you just do that negative b over 2a tricky. So yeah, it's negative of negative 6 over 2, so 3. So this parabola is symmetric around x equals 3. So the restricting domain here would be everything from 3 to infinity. On that interval, the function will be invertible. Does that make sense? I didn't even graph it. I don't know how high it is. But I know that the x coordinate is at 3, so that's the axis of symmetry type of thing. Yeah? Well, I mean, this is what we did. If I just graph that, what was my function? X squared minus 6x plus 3. Here's the graph, right? It's not one-to-one, but what we did, we cut it at 3. And we just took the right stuff, the right part of it. This is the part that we took. From 3 to to infinity. That's our domain restriction. Made that function 1 to 1. We see this becomes really important for those of you who are going to go into pre-calc, which is what? Who? All of you, right? Same book. You don't have to pay anything else. You already bought a book. We see functions like this a lot. You know, one of them, you know, this little guy. Some of you know what that is, some of you don't, doesn't matter. This function always bounces between +1 and -1, and it has some fancy points here. That's a pi, that's pi/2. I just happen to know that. You will know that too. Some of you know that already. And this function does this forever and ever and ever, always stuck between -1 and 1. Is that a one-to-one function? I mean, no, it fails the horizontal line test miserably, right? It will hit a horizontal line at infinitely many points. But we really like to be able to invert this function because eventually we want to solve equations that involve this function. So what we did, we just cut a piece of that function that stays 1 to 1 and spans the entire range of this function. The range of this function is from -1 to +1. So we decided to take this little chunk from this point to that point. So we restricted the domain of this function from -pi/2 to pi/2, and then this little portion of it stays 1 to 1, right? It passes the horizontal line test. It covers the entire domain. So we can find the inverse of this function. I can sketch the inverse of this function. And therefore, eventually, I'll be able to solve equations that involve this type of function. So that's the importance of restricting the domain. Okay? Whew. Wow. How you guys doing? Isn't that beautiful? It's fun stuff. I have one more thing. Because you got really good at my game of guessing the inverse now. So here are the official steps. Steps to find the inverse. So you don't have to do that guessing anymore. You don't have to reverse the order and change the actual operations. But here are the steps to find the inverse. So let f be a 1-to-1 function. So here are the steps. Step 1. Oh, you guys out of paper? Yeah, I went nuts on this day. Write y equals f of x. That's the first step. You know, just whatever your function is, say y equals whatever your function is. What did I do next? 2, interchange x and y. So what I mean by that, for every x, put down a y. For every y, put down an x. So that's what we do. Then third step, and this is really where the money is, solve for y in terms of x. And whatever you get there, that's the inverse. Y equals f inverse. Okay, I'm just going to do a quick example where I actually use these steps, and you'll see what I'm talking about. It's the same thing when you were guessing, only it's more of a official. So, for example, f of x, we did something, what is it, 2x cubed minus 7, we had that example, right? Is that close enough? I don't remember, minus 7 plus 7. So here are my steps. Step 1, y equals 2x cubed minus 7. Write y equals your function. Okay? So that's the easiest step. Second step, interchange x and y. So for every x you put a y, for every y you put an x. So for x I put a y, for y I put an x. And then the third step, that's the harder part, is to solve for y. So how would we go about solving for y? What do you do first? What? No, you're thinking about like y-intercepts or whatever. I want to have y equals some junk. At 7, so this is what I'm talking about. The last thing you do here is the first thing you do there. At 7, so it's x plus 7 equals 2y cubed. Then what? Divide by 2. So y cubed equals x plus 7 over 2. And finally, cube root. Y equals cube root of x plus 7 over 2. That's the inverse. Done. Oh, that was brutal.